feature on an explicit example being useful to do something like make optimal universal gates. All right, now let me get back to some more elementary things. So if you didn't like quadratic forms, this is completely elementary, and I'll be able to explain to you what the Riemann hypothesis is very quickly here. So the parity of a number so this is a very important function, and it governs a tremendous amount of the theory of numbers. So this function lambda of n is the following. N is an integer, you factor it into its prime factors, and you count the number of prime factors, and you see if it's even or odd.
The great thing about the Google Career Certificate is no experience is necessary. We are teaching you literally the foundations of project management. If you only have...
That's a very well-kept secret of a number. We don't know how to tackle that theoretically. There are problems with parity and understanding it in the theory of sieves. Computationally, we don't have a quick way to compute this parity without factoring a number quickly. And while I'm a big believer that you can factor quickly, I have nothing to offer. So people who, I mean, if you look on the Wikipedia, it'll say it's very hard to factor. That is the basis of various crypto systems of public cryptography, but there's no theoretical evidence it's hard. So this parity function is very basic, and let's look at it in terms of randomness and structure. So if you let lambda 3 of n be the number of the parity of the number of primes which are congruent to 3 which divide n, then it's a bit small there, but you'll just see it's a periodic sequence. So there's structure, and you see it immediately. But if you look at the number of prime divisors, the parity of the number of prime divisors dividing n, which give remainder 1 when you divide by 4, it looks random. So, and the most interesting thing is lambda n itself. So lambda 3 is structured, that's the way I'm presenting this, and lambda n itself seems to be random. And we all believe it's random, and proving any randomness here seems very difficult. In fact, it's believed that if you correlate lambda with itself, so if you look at lambda n times lambda n plus 1, say, and sum it up to n and divide by n, then there should be, so the parity of the number of prime factors and the n and n plus 1, they should be uncorrelated, so that they should be, if they correlated, this might not go to 0. So there's a conjecture of Chowler that this goes to 0. But we have great difficulty in proving anything like this, and it's a tremendous achievement of Matomaki and Radziwiłł to just prove that when n gets large, you don't get as big as 1, which is these numbers are plus or minus 1, so the maximum could be is 1, and there's a number delta of k for a given k, say k is 1, positive, then this sum is actually somewhat uncorrelated, and that's the best we know. So we have no tools to study correlations of lambda with itself. But we do have tools to correlate lambda against other functions which may be of low complexity. That's where the theory is very well developed, thanks to Vinogradov, who invented a method to handle sums which are lambda n times f of n, where f of n is a bounded function, and lambda of n is this parity that I'm trying to understand how random is it. How random is this parity function? And it turns out that if you think of this in a certain way, it becomes very natural. That is, if you assume that the function f of n is gotten from a dynamical system in order to understand this problem. So suppose I have a dynamical system, which means I have a space x, compact space x, and a map t from x to x, continuous map, and then I evaluate, I take a point in the space, little x, and I evaluate a continuous function at t to the n times x. That'll be a bounded sequence that's observed in this dynamical system. So if f of n is of the form g of t to the nx, then there's a way of formulating these kind of problems very cleanly. And it turns out that all the progress we're making is really connected with showing that lambda, which is supposed to be random, we believe it's random, and we can prove sometimes it's random in this kind of setting, is that if the entropy, which is the complexity of f, if that's 0, if the entropy of f of the dynamical system is 0, then that should always go to 0. So you can't read lambda of n, you can't observe it in a system of 0 entropy. since I'm going to explain to you lambda of n, I'll say it right now, it's connected to the Riemann hypothesis. If there were a simple system which could tell me the parity of a number quickly, or in a closed form formula, I would buy it because it's got all the information there. It would be a simple system. Unfortunately, the only thing that we are able to prove, and there are a tremendous number of theorems of this type, is that this disjointness conjecture is true. That is that the randomness in lambda is shown to be more prevalent by showing that it's disjoint from more and more zero entropy systems. And each time such a thing is proved, it usually comes with a very nice theorem about primes. So it's usually hard-earned with applications. That's what we can do. If you ask just about thinking of the parity, and I look, it's plus minus 1 at random, and I added those numbers up to n, I would expect that to cancel about square root n if that was random. And that's a Riemann hypothesis. The Riemann hypothesis, which whatever it is, I've now explained it to you in completely elementary terms. It's the sum of lambda of n is at most in absolute value n to the half. And there's always a little safety valve there. Keep it there, plus epsilon. Otherwise, it's not true. All right. You can ask, really, what, with these correlation sums, what's the true size of such a sum? And I told you we can barely prove that that's not as big as the maximum, just slightly better. That was all we know. But there's a model here, and I'm talking about randomness. There's a very good model of how to study these things, and that's to replace lambda by a random multiplicative function. So the most important thing about the function lambda is that lambda of mn is lambda of m times the lambda of n. Because if the number of factors is going to add, and then the parity will be multiplicative. So we could take a random multiplicative function, meaning at each prime, I take the function to be plus minus 1 at random. And this subject of trying to understand the probability theory of such sums and the fine structure of the distribution and central limit theorems goes by the name of multiplicative chaos, which is a very active area.
Multiplicative chaos.
There are many theorems that have been proved. Harper has made some very impressive
ladies and gentlemen,
breakthroughs. Soundararajan, who is a student of mine and makes him my grand student, as he said. They have some remarkable works on this, in particular proving that kind of sum obeys a central limit theorem.
Princeton University.
If I'd like to be a costume designer who also makes the costumes, is the BFA costume or design?
That theory leads to very sharp conjectures as to what we should expect in the number theoretic world. So the probability theory is often telling us what to expect, but on occasion it actually gives theorems. In other words, you can use the techniques from probability to actually prove theorems, and that's the case. There's this very nice work of Arguen, Burgade, Harper, and Radziwill, which discusses something about the Riemann zeta function, which I'm about to introduce, and it proves statistical features rigorously, which without the probability theory would not be achievable. So the interaction between the probability theory and the number theory is more than just to guess what the answer is or to interpret the answer, but also to prove theorems. I'll return to that.
Yeah.
Okay, so what is this Riemann hypothesis that Paul Cohen was saying, so many zeros on the line, what should I take that to mean? This is one of the main unsolved problems in mathematics. It's one of Hilbert's problems. I told you, Paul solved Hilbert problem 1. He also wanted to solve Hilbert problem 8. That would have made him rather unique. So this is considered a major unsolved problem. So I gave you an equivalence of it in the previous slide, 2 slides ago. I said that if you take this parity function and you see how random it is, this is equivalent to it. But this is hardly a way to understand anything. And this is hardly the way that Riemann made this great conjecture. So Riemann sort of developed complex analysis for this purpose. And then, of course, complex analysis became, but this was one of his insights in the theory of entire functions. So if you take the sum of n to the minus s, when real part of s is bigger than 1, that converges and defines a nice function of s. In the subject, I always make this joke, I get proofs, I get 5 or 10 proofs a day of the Riemann
They're
hypothesis.
never funny, Pete.
If it's right, if the proof is zeta of z, because usually when you have a complex variable, you call it z, then I know the person is either done something fantastic because they've never read anything, but it usually means they're just looking at this from a very naive point of view.
Yeah, well, that's what
But
I
I've
do.
always said that if one of those
And
proofs,
that is
if one of those papers
fantastic
give a proof
way
of the
to do
Riemann
it.
hypothesis, then we'll all start writing zeta
may
of z,
be
not zeta of s. But we all follow zeta of s
mathematics
because that's the way Riemann wrote it,
Princeton.
and all followers. So the sum of n to the minus s converges, and the connection with the prime numbers is that this infinite product, if you expand it out by the inverse binomial, that's an identity where it converges, and then it makes sense for all s. And Riemann discovered that if you multiply zeta of s times gamma of s times pi to the minus s over 2, gamma is a nice function,
house,
pi to
ladies
the
and
minus s over
gentlemen.
2 is a beautiful, it's an exponential function. That this
sitting
new
here
function
right
of
now,
s has a fantastic symmetry.
watching.
It extends to the entire complex plane, and its value at 1 minus s is equal to its value as s.
Nowadays,
Called the functional equation, and generalizations of this is what comes from the theory of automorphic forms. It's one of the reasons the theory of automorphic forms is so
ladies and gentlemen,
important.
you see this.
Anyway, Riemann, why do we call it a hypothesis?
Yeah,
Riemann,
that's,
usually you
that's
conjecture
where
or
can
you
put,
ask.
the
But he
randomness
hypothesizes because he wants to
there.
prove the prime number theorem. So he says that if he's checked the first few zeros that people didn't know, but he invented a method to check the first few zeros. The first zero, so the conjecture, the Riemann hypothesis that he makes is that all the zeros have the real part equal to a half. So if I write the zero as rho
trivial.
as beta plus I gamma, then the real part beta is a half. The gammas are very interesting. So he computed the first zero, it was about 14, and he had to invent something very clever to actually be able to do that with a pencil and paper. But he does that. And then he says
do it
that
with
if
a
all these
computer,
zeros lie on the line
Peter.
a half, that's
I
how I'm
do
going to
it with a
hypothesize
computer.
this, then I can solve this problem that Gauss raised, which
use
is
pencil
the prime
and
number
paper
theorem.
like you
That
do.
was his aim. That's why he made it. And he said, I'll return to it because it looks
Why
like
don't
it
you
should
get
be
into
true.
the 20th century?
And that's the famous
or the
Riemann
21st
hypothesis.
century as it is
And
now.
we know millions of zeros, people are computing them all the time. They don't obey any obvious formula, what randomness laws, and it's here that the randomness is very suggestive. And let me tell you what that is.